It's a great pleasure to me to present Laura in this workshop. Laura is professor of physics at the University of Gabriele D'Annunzio of Chieti Pescara, and there she leads the Mambo Lab, the so-called Mambo Lab. And today we ask her to provide an overview of the application of connectivity of the metrics and the methods that Guido Nolte introduced before. And so thank you very much for accepting this. And please, Laura, the stage is yours. I think we have stolen the screen from you, so you have to share it again.
Sorry.
Because we put the screensaver during the break. Okay,
so
thank you very much.
Something similar to the screensaver, but not the screensaver.
Yeah. Thank you very much.
Okay, so thank you, Sara and Alberto, and all the organizers of this very nice workshop today. As Sara introduced, so my task today is to present you some works regarding the use of methods for functional connectivity, really mainly based on the work that Guido has done before, before us, and that I had the opportunity at the beginning of my career to interact with. So more specifically, I will give a very brief introduction from a different perspective than the methods perspective to functional connectivity in MEG and EEG. And then I will go to a slightly narrower topic that what Guido has presented, which is same kind of methods, so based on the imaginary part of coherence, but for more than one signal or more than one pair of signals. So we will call them in this framework the multivariate methods for functional connectivity. And then these will be the methods used in some of our studies, and will be an interleaved presentation between methods and applications. Finally, I want you to show and to introduce, if I have time, some very recent work that we are doing in a framework of neurostimulation and connectivity. So, okay, I guess many of you know that we are working with functional connectivity when working with the EEG and MEG. And functional connectivity basically means that we are studying brain connectivity in terms of statistical dependencies from our functional data. So functional data can come from a bunch of invasive or non-invasive techniques. And of course, what we are presenting today mainly deals with the use of MEG and EEG in this framework. Okay, I have some introduction here also which pertains to the use of fMRI to study functional connectivity. And that's mainly because some application that you will see later on also aim at addressing frequency specificity of some results that have been obtained before with fMRI. So the idea that with which fMRI came out, and that is based on concepts similar to amplitude envelope correlation that Guido introduced before, is that if you in this case take the univariate signal, which is given by the percentage bold change at one brain region, different brain regions behave differently. So some of them are activated when others are deactivated, and so on and so forth. And if you study correlation between these, you can derive the so-called resting state networks with different properties, and have been associated starting from resting state also to different cognitive tasks and so on and so forth. There are, many different networks with different functional roles. But as I said, having said this, now we want to concentrate ourselves on MEG and EEG, and we all know that what these two techniques can give us is, on the one hand, the magnetic field, and on the other hand, the voltage difference at the scalp level generated by neuronal currents. And this is, of course, something that we can exploit in order to derive, similarly to what was done in fMRI, in order to derive brain level information by first solving an appropriate inverse problem, so going from sensors to sources. Of course, as Guido was mentioning before, this is one option, going first to sources and then calculating connectivity, but we have other options, so to project connectivity from sensor level to source level, but here I will like go through the more classical pathway, which is from sensors to sources and then to connectivity. So, and we can then derive connectomes, which basically represent interaction between all possible regions in which we parcel our brain according to some of the metrics that we have seen before. So the first difference that we have with respect to the idea of brain networks in fMRI is the temporal resolution of the signal, which is in the order of seconds for fMRI and in the order of like milliseconds for MEG and EEG. And as Guido already mentioned, the part that is has been shown to be more related or more similar, I'd say, to the fMRI part is this amplitude envelope correlation concept, which is not what we are going to focus on today. So what we will try to assess in our data is the relationship, the phase relationship between the underlying oscillations that you see here on the right, that are derived from two brain regions, such as the blue and the red one. So why are we interested in these, other than from a pure mathematical and methods perspective that has been already addressed before by Guido? There is also another side of the story which can make us be interested in this kind of metrics for assessing connectivity, and that comes from models about brain functioning. And one of those that goes very well with this idea of phase differences between brain region is the revisited, I would say, communication through coherence hypothesis. So if we assume that two brain regions like red and blue as before are synchronous, so their oscillation are locked somehow, then this is a proxy for the two brain regions to communicate one with the other. On the other hand, if we have, in this extreme case, if we have counterphase situation, then these two brain regions are prevented from communicating one with the other. And communicating basically means that the one region will send spikes that will arrive at the maximum of the excitability state of the receiving region. So based also on this neurophysiological hypothesis and observation, we can use the metrics that have been addressed before to understand whether these two oscillations are aligned somehow. And aligned doesn't really mean that they perfectly have to have zero time lag with respect to the others, because the brain really needs some time for the signal to propagate from one region to the other. But it means basically then the phase relationship between the red and the blue regions is constant, or is stable across time, I would say. If we, on the other hand, are in the opposite situation, then what we would observe between the blue and the black regions is a phase difference which is scattered all over the angles that the phases can span, like in the bottom situation. So I don't think I still need to introduce the idea of the imaginary coherence, which was introduced by Nolte and has already been mentioned to vanish for independent sources. And this is, I think, really something useful when you want to investigate coupling, phase relationship and phase coupling between brain regions, try to get rid the most that you can of volume conduction. But this measure, together with others that have been also developed by Guido, such as the phase slope index, which basically is able also to characterize in the same framework the directionality of interaction, assessing who is the leading or who is the following area in a pair of two. And this is based, on the slope of the phase, as the name already says, as a function of frequency. So all these measures, which can be very nicely used, they all assume that you are dealing with two signals. So these two signals can either be the signals at channel level, but these two signals can also be source level signal after you have like made some assumption, for instance, on the forward model of the brain of a subject, which makes your signal to be represented only by one number that varies over time. So what we did with Guido in the beginning, and then also like later with the PhD thesis of Alessio Basti, which we'll tell more this afternoon about this, is to like work on an extension of these bivariate methods to the multivariate case, where, as I said, multivariate here basically means that you can have a method that deals with a set of signals at one region and a set of signals at another region. And these sets do not need to be equal in number, although my showcase is here represents a situation in which they are. So usually what is done in the MEG and EEG field is that if you are in this case, for instance, by solving your inverse problem on a source space, which is a grid with no prior assumption on the direction of your current, then what people usually do is to use some dimensionality reduction step in order to extract the dominant signal. For instance, this is achieved by PCA or this kind of methods. And then to use bivariate methods as if we add really one signal at that very same location. So I'm not going into the detail of why, I mean, this could lead to overlooking part of the coupling that we have in the brain. But I'm just covering like the idea that, okay, so you could avoid to do this step of dimensionality reduction. And in principle, you could think that if you have many with many, you could do all possible pair combination and then average across all possible pairs. Okay, yes, there should be an animation for this. But then if you do this, what it turns out is that the result might depend on the reference system in which you are projecting your data. So it can be like, can be an issue if, for instance, you have a different situation in which your data are projected along different dimensions. So I'm starting from like the one that came last in the story, which is the version, the multivariate version of the phase stop index. And the idea here, as was done before also for the imaginary part of coherence, is to apply a spatial transformation that can be applied to your original time series and make them as such that when you do this all-to-all possible combination and an average, then your result will not depend on the reference system that you are using. So in practice, you can like derive this transformation, which is derived in this case in the paper from Alessio Basti. But in practice, this means that you do not really need to apply this transformation to the data, but there is a proper combination of cross spectra that applies this transformation to the data for you. So the output of this will automatically not depend on the reference system that you are using for. I'm not really describing the details of the equation, but if you are interested, I mean, I'm here, Alessio would be here after me, and we can go into that. Just that here R stands for the real part, as before in Guido's talk, and I stands for the imaginary part, and the F plus the F is the frequency plus the frequency bin across which you calculate, you estimate the slope that is needed to assess whether signals at location 1, in this case signals at location K S come before signals at location K. So, okay, of course, in the paper we had to do some simulation to show that this worked better than what. We had several examples here. I'm just showing the option in which you assume that the transformation is made by applying first the canonical correlation analysis to your two subspaces and then applying phase slope index to resulting direction. And what we observed is that okay, if you simulate like several situations in which you have two correlated multivariate sources and a bunch of uncorrelated sources, then usually the multivariate PSI is able to detect more situations in which the sources are really correlated. But this doesn't mean that the other methods, so the canonical correlation, is providing wrong answers. Rather, it means that the canonical correlation provides more uncertain answers in a statistical sense. So it's like if the method really can boost the statistical properties of your results and provide you with something that you can easily assess whether it comes from correlated or uncorrelated sources. Like for the applications, we started with the data from the Human Connectome project, the MEG ones, which are quite a nice number of subjects doing resting state in this case. And I recall here the idea that comes from fMRI, so that if we have resting states, so we should have something that resembles these kind of networks, at least I would say some specific frequencies that of those that we can like sample with our MEG or EEG. So what we observed is that, for instance, if we seed the visual cortex, then you will, like the method will, this is, sorry, average across 61 participants, and each of them was performing 5 minutes of resting state with three blocks of 5 minutes resting state with fixation. And what we observed is that there are sources that precede V1, so the activity of which precedes V1 in the alpha band, and sources the activity of which follows V1. And for instance, the parietal sources seem to exert, if you can like interpret this as a temporal preceding, as a top-down drive from parietal to visual cortex, then this seems to be the case. And it seems to be the case, so for something that is similar, for instance, to the relationship that one can imagine to be between the visual cortex and what is called the dorsal attention network. That is a network which is recruited when subjects basically have to pay attention. So it's kind of consistent that the attentional system is engaged prior than the visual cortex. On the other hand, we also have coupling with parts of the what is called the default mode networks, like this blue spot on the medial frontal part of the brain, and so on and so forth. But I won't go much in detail of the interpretation of this. What I want to show is the comparison with the canonical correlation analysis. As I said, it's not that we are seeing something completely different, so it's not that one method is right and the other is wrong. But it seems that what we see, we can see it more robustly. So consistently with our simulations, it seems that, for instance, if we have to go to, if we would have a lower number of subjects, or even at the level of individual subjects, we could be more able to observe a phenomenon that otherwise could be masked to our observation when using a different approach. Okay, and this is basically the same story made by another guy in the group of Guido, Arne Ewald, for the imaginary part of coherence. And also here you have a different transformation, and the transformation plays the same role on your data. And finally, you can come up with a compact measure which uses basically the imaginary part of core spectrum weighted by the real part at the denominator, similar to what happened for univariate cases in which we had the ratio with the power. Here we have something which is similar to that, but which takes care of the full subspace, which is represented by source S or K, so something which is like 3 by 3 or 2 by 2, or depending on your subspace dimension. Also here, we applied this method to resting state data. These are different data, I mean, from a historical perspective, this study comes earlier than the other one. And here the question was exactly the one that I posed before. So shall we be able to see with MEG something that shows the frequency specificity of the brain networks that had been observed with fMRI? So given this question, we really decided to lock ourselves to specific nodes of those brain networks, which are, some frontal part and some parietal part, and to look at the conjunction between the regions in the brain which are both coupled with both these two seats that we are looking at. And we have, of course, all the different frequency bands. And what we could observe at the time is that the lower frequency bands, such as the delta band, resembled the contralateral part, contralateral to the seats of this dorsal attention network, but also in the alpha band, we could observe some features which were possibly attributable to this dorsal attention network. But we also had the visual system, and in the beta band we had beta index. And I must say that, of course, we started the game by, although I don't have a direct comparison, but we started the game also with other metrics, and we really, in this resting state situation, could exploit more out of the data by using the multivariate approach, exactly as it happened later for the face-up index case. Now, this is a bit more fancy, I'd say, because we also applied these methods to study not really resting state, but something very close to it, which is meditation. So meditation is, again, a continuous brain state in which basically the subjects are doing nothing but meditating, whatever this means for our brain to meditate. In this case, the subjects were really experienced people because they were monks. And so we wanted to study them in MEG and with different meditation styles, which are either more internally driven or externally driven, and make comparison between our frequency-specific connectivity maps. Also here, it's a simple study, it's seed-based, and in this case, it's seed-based to one of the nodes of the default mode network, because basically what is going on in meditation is that there is a kind of observation of your internal state and try a tentative of refocusing on your internal state. So basically this default mode network, which is known to play a role in the internal memories and recalling and things like that, could be a good candidate for us to observe differences between the conditions. And this is basically what we did. And so we observed differences with other nodes in the default mode networks, and also with nodes that, that belong to other networks, such as a frontoparietal network. And what is nice is that depending on the networks, we observe the different shape or slope of the correlation between the expertise in the monks and our connectivity. So meaning that, for instance, when the internal relation with the other parts of this default mode network were lower, the more you had expertise in meditation. So basically, this means that you are able to focus more on the state and less being distracted by yourself. Okay, then we also applied these methods to task-based data. And basically, I'm showing, I think, two examples. One, which I will describe a bit more in detail, and the other one, which I will go on after this one. So this one is the classical, I would say, Visuospatial attention task, which we borrowed basically from the group of Ole Jensen, at the time when it still was at the Donders. And there was a previous study by Tom Marshall, basically exploiting this standard paradigm in which people are asked to attend either left or right. And then they are like presented a cue, which is these Gabor patches that you see either horizontal or tilted. Then you have to respond. Task of the subject was to respond to whether the orientation was rightward or leftward. Anyway, this is a very typical task that is used in all those studies that investigate the role of alpha rhythm as an hallmark for attention. So like the inhibitory role of the alpha rhythm in the posterior part of the cortex, so in the visual cortex, which seems to be like really a hallmark for attention, meaning that when you attend to one side, there is like an enhancement of alpha in the ipsilateral hemisphere, and there is a reduction in the contralateral hemisphere, contralateral to the attended hemifield. So basically contralateral to where these arrows are telling you to look at. And this was a classical, I would say, power modulation study. And what we did was to try to understand whether we could like assess any kind of relationship with the other areas of the brain. And for this, we used again this multivariate version of the imaginary part of coherence. I'm just showing a movie, hoping it will work. I didn't actually try, but usually works. And you will see on the left the coupling of this pink area here on the bottom, which is the visual cortex, to the rest of the brain in the alpha band. And on the right, you will see the task going on as the subject sees it when it's inside the MEG scanner. So, okay, and of course, this is averaged across trials. So we only see like the modulation with respect to the baseline across trials. We are not expecting single trials of the study. So, okay, you can already see that there is some involvement of the occipital and of the parietal areas, and this involvement seems to be specific depending on the phase of the task in which you are engaged at the moment. So if you consider the whole period, which is, sorry, I go back for 1 second, which is the one between the visual cue presentation and the response of the subject, basically the target presentation, what is usually called cue target interval, in which the alpha power modulation is usually observed. Then you see, that there is a coupling of the visual cortex, which is the black dot on the visual areas, to the parietal cortex, and that this is specific to the hemisphere, which is ipsilateral to the hemifield to which attention is allocated. And this is true, of course, for attending right and for the attending left location. So then, but we asked ourselves whether, okay, we started with alpha because alpha is known to be involved in this attentional mechanism, but do we see more than just alpha in this study? And the answer, at least to our case, for those two regions, for the parietal coupling to the occipital cortex coupling, the answer is basically no. The only thing that we see is a modulation in the alpha frequency band, and but nicely, what we do see is that this modulation is really specific of the hemisphere. So if we move to the other hemisphere in the condition in which you are supposed to attend right, and you don't see this modulation, and the same like in a cross style, so you see it only when it's ipsilateral to the attended location and not in the other case. But what is nice, I think, in this study, beyond the study of the attentional mechanism, is that we used these functional connectivity results also to understand whether they had a behavioral and other kind of relevance in our subject. So the first thing that we did is to use the DTI data present in all these subjects, for which we add the volume of the superior longitudinal fasciculus tracts, which are basically the cyan, blue, and pink tracts that you see over there in the brain, and which connect parietal, which is here, occipital, which is more here, and frontal parts of the brain. And we try to assess whether there was a relationship between the functional connectivity and the anatomical connectivity. And what we observed is that, okay, it's not the connectivity itself which is related, rather it's hemispheric asymmetry. So basically, if you take one of these scatter plot and you look at the rightmost point, that means that when asymmetry left minus right is positive, so when one subject has more modulation of connectivity with attention in the left hemisphere than in the right, then for that subject also this fasciculus is larger in the left hemisphere than for the right. So the difference left to right in the functional connectivity is related to that of the anatomical connectivity, not for all the three tracts in which these fibers can be dissected, rather only for the first and the second, which are known also to to be involved in this kind of attentional tasks, and which apparently for what is fiber tracking, like ability to detect the starting and the ending point of the connection, apparently are more strongly linking the parietal and the occipital regions, which we observed. And also, as I already mentioned, this very same asymmetry of functional connectivity is also related to the ability of the subject to perform the task, meaning again that when a subject has more connectivity modulation on the left hemisphere, then it will be also better at responding in terms of accuracy to targets presented to the left hemifield. And also what we used here is this bicoherence, because we were a bit puzzled that these brain networks also have quite important frontal part that we were hoping to see either in alpha or in other frequency bands, which we explored, for instance, in beta, but we really didn't observe at the very same frequency. So we asked ourselves whether it could be that this relationship of the frontal to the parietal and occipital part is more like a kind of a cross-frequency coupling. And for this, we exploited the bicoherence that Guido was mentioning before. And I'm not showing the results, I'm just showing, a putative interpretation of what the bicoherence told us. So one option to interpret the results that we got, that seems to be the more consistent with the neurophysiology that is undergoing this kind of cognitive mechanisms, is that we have like kind of a top-down drive of the frontal frequencies, which are working at the beta rhythm, and this engages the parietal regions, which we have seen to have like an alpha rhythm involved, but our cross-frequency measure also told us that they also have a beta frequency involved. And so on turn, these parietal these parietal regions might be the ones that are like interacting with the occipital frequency, with the occipital regions at the alpha frequency. Sorry, it's difficult also for me to put together all of this. And but the nice thing of this was that also this was somehow consistently modulating with the side of attention and with the hemisphere. So where you see the larger arrow, that means that in that hemisphere for the attend right location, we had a larger effect for this coupling. Okay, and this was like our task study using this imaginary coherence multivariate version. But also, what I want to highlight now is that this kind of multivariate metrics can be very useful also when you want to work with parcel data. So imagine that you don't want to have like a dense connectivity map in which you have thousands of locations in the brain at which to sample your signal and then to calculate connectivity. And in our previous examples, at each and every location in the brain, we had like 2 or 3 possible components of our signal, which all contributed to the connectivity with the rest of the brain. Now the story is simpler on the one hand because we have less brain regions. So this is just one example of a 400 parcel parcellation from Yale, but the story works for all parcellations. And so on this end, it's simpler because you have less points like in the brain to for which to assess the connectivity. On the other one, it's more complex because at each of these ROIs in which you discretize your brain, you have many signals, possibly a different number depending on several factors. One of these might be the size of the parcel that you are considering. And if you want to study connectivity, again, it can be even more struggling to find only one direction which explains all the signal contained in all of these parcels. So the idea is that you can use this multivariate matrix to maybe like study the coupling between this multivariate time series or multidimensional, if you wish, time series in a similar way to what we did for our resting state data in the BASI study, or like that kind of approach in which we also were looking for the directionality of the information. So in this case, we used again the data from the Human Connectome project, but this time we used another set of data, which is task data, which are the working memory. In brief, the subject is asked to to perform the task in 2 different conditions. Condition 1, which is the one that you see on the bottom, you have a reference image presented in the beginning, which is this smiling guy here with the gray frame. And then after a fixation block, you are presented with a new image, and you have to recognize whether the currently presented image matches the first image that was presented. So the matching is always asked to the subject between current and first. While in the more difficult condition, which is the one that you see on the top, the structure is similar, but the subject is asked to assess whether the currently presented image matches to the images presented 2 images before. So in this case, this green frame here states that, okay, this is target, so this is what you should, when you should press your button, because this image really resembles the one that you had to before. And then the same for the very last one, which is target, since if you go 2 steps before, then you see the same image. So what we did here was to use the multivariate PSI at the level of parcels to assess, first of all, to assess whole-to-whole, like parcel, all parcel to all parcel brain connectivity, and then to ask a support vector machine to classify between the 2 conditions, so the difficult and the easy, the 2 back and the 1 back, in the different frequency bands, meaning that connectivity was calculated in each of these frequency bands, so theta, alpha, beta, and gamma. And okay, so you see that like gray dots on the top mean statistical significance of classification as a function of a parameter of the classificator K, which we don't need to go into the detail. But like the take-home message here is that we could see some above chance classification in the theta and in the alpha band. But then we asked ourselves, okay, so what if we now ask the classificator to to process the whole information provided by all the whole-to-all connectivity matrices at the different frequency bands. So we give all of them to the classifier. And basically what we see is that some of these combinations, for instance, the red and the blue, they do provide a higher accuracy of classification with respect to the other situation. Of course, this is not only due to the increasing number of features that we provide the classifier with, because this is not true. And we have, I mean, I'm not showing here, but we have counter examples with the same number of features and different frequency bands, which nevertheless did not increase our classification accuracy. So, of course, also here you can, after having performed the classification, you can ask which are the connections which were really crucial for distinguishing between the two conditions. And also here you can, of course, assess functional significance, for instance, to the theta band in the frontal part of the brain, or also if I go here to the alpha band results that we have in the posterior part of the brain, which again is something parieto-occipital with possibly some involvement of attentional processes that are required by this kind of task. Okay, so this is basically the part of the talk in which I showed what we have done in the most recent years, I would say, with this kind of phase coupling metrics, and more specifically focusing on those in which we have used their multivariate version. Then, last but not least, I want to spend a few words on what we are involved into now, which is this ConnectToBrain ERC synergy grant, which sees basically Aalto University, Chieti University, and University of Tübingen involved, in which, again, based on this idea that, okay, so phase relationship and time delays are important for the brain communication, we want to also use neurostimulation and specifically TMS to interfere with the brain functioning and to see how this propagates across the brain. This is not, I must mention for those who are familiar, this is not the idea of inhibition through repetitive TMS, but it's really using TMS as a probe for calculating or estimating effective connectivity and relating it to functional connectivity. This is very similar to what Paolo Berardinelli have been presenting the other day, and he has shown that there is evidence that if you provide the stimulation when the brain is set in different states, then the effect of the stimulation is also different. And that if you target on specific brain states, then the effect will be more reliable, meaning that the subject will show more similar effects than if you provide the stimulation at random phases, in that case, of the oscillation of your target node. Here and in the project in general, the idea is a bit more ambitious because we want to track in real time not only oscillations at one location, but we want to track connectivity at the best that we can, given the amount of data that we need for estimating minimally reliable connectivity. And we will use real-time tracking on connectivity and multi-locus TMS that will be developed in the project, meaning that we will be able to target not only one location at a time, but more than one brain location. So in principle, if we see that two brain regions are connected, and if this makes a difference for us for the impact of the stimulation, then we could stimulate not only one of the nodes of this connectivity, but if we think that's important, we could stimulate 3 at a time or even more, or give some sequences according to the phase difference between the different brain regions can deliver a sequence of pulses. So our connectivity will have here basically two roles. One is to help in assessing where to stimulate, and the other one is to help in assessing when to stimulate by streaming our EEG data and looking for specific conditions. Now, the thing is that, and this is the idea. So this will be done in a closed loop. So the idea is that, we have some connectivity in the brain, then we come with the stimulation at one or more sites, and then this will change the brain state, and we could either measure the changes and relate them to the connectivity before the stimulation, or as in this case, we will measure like changes in the periphery, not in the brain itself, so like MEPs that Paolo was also showing, and trying to understand whether changes in MEPs is related somehow to our connectivity state before. As I said, this is, it's still really a starting work, and we need to understand what are the connectivity features that, and if there are connectivity features that can predispose the brain in such a state that it's more effective when stimulated at one or more locations. For now, the only thing that I will show is that, so the first thing was to try somehow to understand whether connectivity before the stimulation is related to what happens in the brain at the peripheral level, so to the MEPs after the stimulation. And this is one example in which we seeded the M1 and we mapped connectivity. Of course, this is not real time, sorry, I forgot to mention, but it is previously acquired data in which we have 1,000 trials per subjects, and in those trials we have, of course, EEG, pre and post stimulation, and we have amplitude, peak-to-peak amplitude of MEPs, so this muscular response at the contralateral hand with respect to the stimulated hemisphere, which is elicited by the stimulation itself. So it's something that is the output of the stimulation, I would say, at the peripheral level. So what we did was to assess connectivity with fM1, which is the target of the stimulation, with the rest of the brain. And what we observed is that connectivity is present only with the premotor region. And that is to some extent, which is basically similar to the extent that is known to be involved for the relationship between phase at a given location and MEPs. So connectivity also to some extent explains the variability in the MEPs that we see. And this is, this is true for these regions if we see the left hemisphere, and there is also a bunch of regions if we see the right hemisphere, which at the mu rhythm, which is the very same rhythm that is usually used for this closed loop stimulation, elicits or at least explains part of the MEP variability in the data. So the idea is that if we are able to to show that post hoc in these subjects and in all this set of trials, we have that these connectivity changes have something to do with this MEP, then possibly it would make sense in real time to stimulate those regions that appear to be related to the site of our stimulation. And okay, so I'm basically done. So I think that the conclusion that we can derive from my talk today is that although very different from those that maybe many neuroscientists are used with, we can derive connectomes with EEG and MEG. And these are, of course, spatially defined, maybe less well defined than fMRI, but still with the spatial specificity and with the temporal specificity, such as that shown in our, for instance, visuospatial attention data, in which we have observed that these quantities vary depending on the different phases of the task. And these phase difference metrics not only have very nice properties in a mathematical sense, but they can really be able to target some putative mechanisms for frequency-specific phase coupling. And in some cases, these multivariate approaches can be more informative, at least can take into account the whole information that is in the data. And finally, with like the direction that we are taking now, and also with other previous studies with like modulation induced, for instance, by state changes in meditation, I hope that you like believe, as I do, that these MEG and MEG functional connectomes are potentially useful markers of brain state changes and can be, for instance, like of aid to neuromodulation or neurostimulation in general. So with this, I want to thank all of you, of course, for your attention, and the guys from the Mambo Lab here, who, I mean, did the most of the practical work, and Vittorio Pizzella, who is always like supporting and being co-PIing, I would say, the group, and Guido, of course, for having introduced me many years ago to this like field of functional connectivity, and Romani, Ziman, and Ilmo Liemi, who are the PIs of the ConnectToBrain project that I mentioned in the last part of the talk. Before I leave it to any question that you'd like, I'd like to advertise that we have like the ConnectToBrain project, but also another like grant to study models of brain connectivity in meditation, and we will soon open the positions for that. So if there are students that might be interested, we are more than welcome to welcome them. Thank you.
Thank you, Laura, very much for this very nice and inspiring talk. Let me check if there are any questions from the audience.
Do I have to raise my hand or something?
No, you can go ahead, please.
Okay, many results, Laura. I'm impressed. But
I mean, you are co-authors in many of them.
but not on all these experiments.
Not on all these.
So you had this. First of all, I comment the multivariate measures for MIM, what we more use. I can confirm that this, I think it's better than a bivariate measure. It's much more stable. And also for the bicoherence, but that wasn't multivariate, was it?
No, that wasn't. No, that wasn't.
It wasn't. So you have plans to do this in multivariate version to make out of it?
I mean, not sure. I mean, that would be really nice. And actually, yes, we have also been like discussing this, for instance, with Ole Jensen, or people who would like to compare it to PAC and to those approaches. But I don't think that we are going to do right now. But I mean, if there is the opportunity, that would be really nice.
Okay.
Let me check if, in the meantime, I also have a question. I actually would like to reformulate the question that Alberto made to Nolte in this way. Do you think that there are any real data that can be used as gold standard for testing new methods? I mean, for example, when you develop a new inverse model, a new methods for inverse solution, you know that, for example, you can use the auditory data because you know more or less where the response are going to be. What about connectivity? Do you think that resting state can be a good gold standard? And for example, do you think that comparison with other modalities like fMRI can be something useful in that direction? What's your feeling? I know it's a tough question.
Yeah, it's really tough. I can borrow Guido's statement. So it's a very good question, but the answer will not be as good. Because, I mean, let's start from the second part. So to compare to other modalities is tempting, but I think that we have a much richer window to which to look at the brain functioning, and that will not always match, at least with fMRI or slower frequencies modalities. Then, of course, if we would have, for instance, ECOG or things like that, then of course it would make sense. But fortunately, I mean, that's a limited set of data, fortunately, for the human being. And so I don't know, I mean, we were, like I was putting it in that way because the Human Connectome project, I must say, that is really fMRI oriented. And so in the beginning, there was a lot of skeptical aptitude with regard to EEG and MEG. And that was mainly because we could not provide the same kind of hallmarks that were like the reference for that community in the brain. So that's somehow the historical reason why in my talk sometimes you see like the comparison, but I really think that what we can see is much more and will be much more, how do you say, disentangled, like these networks will also be disentangled according to frequencies, and so basically not. So for the reference data set, I don't know, I mean, my experience with resting state data is that it's really hard because you have to have good signal to noise ratio. You have to have, like usually the most of what you have seen comes, not all of it, but the most of what you have seen comes from the alpha band. So, okay, maybe if you work with resting state in alpha or mu, as we are doing now, then could be fine. But I think there is much more inter-individual variability than if you have simple tasks as those that you were mentioning. And I don't know if like brain modeling can also provide a reference ground, which is not really real data, but still is something in between the AR models that we are, of the Kuromoto that we are using, and like something which is more physiologically inspired or things like that. But to my knowledge, no, there is not. I don't know what Guido thinks, but there is not reference data for this kind of thing. Maybe, I don't know, something like cross-modal, like interaction, so that you have somehow the basics functioning of the brain, like motor and visual, but you make the protocol such that you know that there is interference between these two processes, and so you might hope to see something that tells you that there is also connectivity, but not sure.
Okay. When you see brain model, you mean simulation, right? So
I mean simulation,
yeah,
but something like I was thinking about, like thinking large scale. So I was thinking about the virtual brain, or
okay,
like
yes.
things like that.
Okay. Thank you very much. Very nice answer to a tough question. Let me check if there are any other questions. If not, I thank again both Guido and Laura, virtual club, and I think we can call the lunch at this time. And the workshop we will start again at 2:30 with a series of short talks again about connectivity mainly.